Hello everyone and welcome to my presentation. I'm Nick and I'm going to be talking about ROP defenses and whether or not we can beat them. So we've obviously talked a lot about return-oriented programming in our class this semester. We've seen how it allows us to circumvent things like non-executable protections and things like code signing and stack cookies. So it seems very dangerous and rightfully so, because I found a statistic that said that in 2016 up to 90% of attacks that were happening we're utilizing some form of return-oriented programming. And we've discussed ASLR and how it might solve the problem by sort of making the memory space more difficult to map. So I'm going to talk about that specifically in the next slide. But if it doesn't work, then what are the other defenses we have at our disposal? And finally, I'm going to sort of talk about how we make defenses non-intrusive. So a good defense against an exploit like ROP requires us to not have to sort of edit the kernel or have a significant amount of overhead that could make it sort of inconvenient for us to use that defense. Now, what is ASLR and does it solve ROP generally? So obviously we've learned a lot about this. ASLR is sort of a memory protection process that guards against buffer overflow and ROP attacks by sort of scrambling the memory space in such a way that it's harder to figure out where the pointers you need are, where the gadgets you need are, so it's more difficult to deploy them. They can, however, be overcome. So leaking even a single pointer in an ASLR system gives up the protection, because it then allows us to sort of figure out where everything is, map the address space, and just do a return-oriented programming attack with the gadgets that we now know the location of. They're vulnerable to just-in-time ROP attacks. So I'm going to talk about that in the next slide, but that's a specific type of attack that ASLR is vulnerable to. So they're an improvement. ASLR is an improvement, but it's not enough to solely guarantee the security of a system. Now, what are just-in-time ROP attacks? So you'll see here a 2013 paper talking about these just-in-time code reuse attacks. And they're talking about it in the context of fine-grained address space layout randomization, which is sort of an advanced form of ASLR where you have, instead of just scrambling the whole address space, you sort of divide it into chunks, scramble each of the chunks so that if one pointer leaks in one of the chunks of the memory space, then that doesn't give up the pointers in the whole memory space. Rather, someone would need to leak a pointer for multiple chunks in order to piece together the layout of the whole memory space. So a just-in-time ROP attack sort of dynamically discovers leaked memory pointers on the fly in these chunks, and we sort of exploit memory leaks multiple times in order to map the memory space, find the gadgets that we need, and then build our exploit buffer, our ROP chain, or redirect the instruction pointer. So things we've seen time and time again throughout the class, just reapplied here in a way that is able to overcome ASLR, or in this case, fine-grained address space layout randomization, which is sort of a more advanced, specific version of ASLR. Now, another defense, shuffler, so fast and deployable continuous code re-randomization. So ASLR is an example of code randomization where we randomize the location of code in the address space. However, shuffler is more advanced than that. It re-randomizes the code in the program every 20 to 50 milliseconds, shuffling the address space so that in the time that it takes an attacker to find the pointers or the gadgets they need, suddenly the address space is re-randomized and they can't deploy them effectively. So this is further abstraction. It doesn't require us to modify the kernel or compiler, which we talked about earlier why that's important, and it runs in the same address space. So it doesn't require a significant overhaul of the program itself. Now, here's sort of a demo of it. In this demo, you'll see these sort of hashtags, which represent the code in the memory a typical web server is running. And you'll see here they're all static, but when we employ shuffler, they start to move every 50 milliseconds. This sort of demonstrates just the constant movement of all of the code in the memory space, and you can imagine why that would be difficult for an attacker to deal with. Obviously, you find a gadget and suddenly, oh, the gadget's over here, the gadget's over here. It's really hard to deal with that. And so this is one example of a defense against ROP that could potentially be effective. Now, that paper was written in 2016, but if we skip forward 1 year to this article, The Dynamics of Innocent Flesh on the Bone, Code Reuse 10 Years Later, you'll find that there's multiple strategies for defense that they discuss. There's control flow integrity, which ensures only legal targets allowed by what's called the control flow graph are permitted. There's information hiding, so that's like ASLR, fine-grained randomization, the things I discussed much earlier. There's re-randomization, aka shuffler. There's pointer integrity, where we sort of like encrypt pointers and try to stop attackers from tampering with the pointers in the first place. So there's all of these things, but what this article found was that they were able to build an exploit that could overcome these defenses. So it's called Newton, and what it does is it dynamically figures out which defenses are being used in the system. So is it running a version of ASLR, fine-grained address layout randomization, re-randomization, whatever that might be, and it sets whatever the defenses it finds as constraints to the model. And then it automatically generates gadgets that are able to comply with these constraints. So it has various ways of overcoming something like re-randomization or ASLR. And once it figures out which defenses are in place, it will use those algorithms to try automatically generate gadgets that are able to comply with the constraints set earlier. And so this is a clever way of sort of automating the process of exploitation. And they tested it on 3 popular web servers, Nginx, Apache, and LightTPD. And they looked at whether or not they were able to overcome defenses, and if so, which ones. What they found was that switching to dynamically analyzing constraints actually significantly aided in the discovery and use of gadgets. So they were able to find and circumvent these state-of-the-art defenses by using this sort of automated approach to a model that has constraints on it. And what the conclusion of their article really was that ultimately, to sufficiently reduce the risk of an attack, you need to combine multiple state-of-the-art code reuse defenses. So you need to have multiple of these things like ASLR, pointer encryption, CFI. You need to combine them and use them in your application in order to ensure that the necessary resources to be able to successfully discover and exploit each individual defense reaches a level that's too high, and thus the attack is no longer worth doing, or it becomes too difficult to do. Now, to sort of wrap up the discussion of this article and the presentation generally, I want to show a quick demo of the Newton in action. And I'm not going to describe exactly every command they're typing in here because it's very complicated, and frankly, they don't describe it very well. But what they're doing here is a proof of concept attack against Nginx to demonstrate that they're able to bypass CFI in the web server. So they have these 5 terminals. Terminal 1 seems to be running Nginx server with GDB so that they can sort of read, write, and inspect the memory of the web server. 2 seems to be, the top right corner seems to be sort of sending requests to the server and preparing the program state. So they have Newton running, and part of Newton is that you need to send a bunch of requests to the web server to start figuring out which defenses are in place. And 3 through 5, these bottom right corner terminals seem to be doing a similar thing. So they're sending these parallel requests to sort of figure out and record various information about the address space and what defenses are in place. So while I'm not going to go too into detail about how they do this, what it ends up happening is that they're able to successfully bypass CFI, which is interesting because we talked earlier about how it's one of the state-of-the-art defenses in place. So what this article and sort of more generally my research for this presentation has led me to believe is that in order to have good defenses against ROP, you need to not only have a good combination of all of these state-of-the-art defenses, but it's potentially necessary to invest in more heavyweight defenses that take more overhead. So if you're securing data that's very important, you want to not only have a good combination of re-randomization, CFI, pointer encryption, some version of fine-grained address space layout, but you're also going to want to look into employing more heavy-duty approaches or innovating in creating new defenses in order to keep up with the new wave of ROP attacks that are always coming at all times. So to sort of round everything out, there's obviously no way to predict exactly how an exploiter is going to get into the system. We saw in 2016, Shuffler was proposed as a way to do this. They thought that it was a really good defense, but simply a year later, hackers or researchers were able to figure out a way to automate and exploit systems that had re-randomization turned on, which means really in order to keep up with the constant string of attacks that are happening, we need to come up with some new defenses and really innovate in the space. So thank you very much, and I will answer any questions.